In the 5th grade science standard for the state of Texas, 5.2D states that students are expected to analyze and interpret information to construct reasonable explanations from direct or observable and indirect or inferred evidence. This one student expectation, or SE, can cause some of the greatest challenges for students due to what it entails the student to do. If a student has only been a passive receiver of scientific knowledge, they will not have the ability to draw from prior experience of active investigations. In order for a student to be successful, they must engage in the entirety of active investigations, which require them to practice these skills of observation, inferencing, analyzing, and interpreting. Even doing so-called cookie-cutter labs over and over may not yield the benefit of actual student-led investigations. From my personal teaching experience as well as observations of hundreds of science classrooms, it is the rigor and challenge of students struggling with engaging investigations and their teacher guiding the process of thinking that will yield the greatest success on this most valued standard. Simply put, students must do real science, struggles and all. To begin with, we have to look back at the previous student expectation that requires a student to collect data through observation, which of course could be done with all 5 senses. We have to remember that the words data, evidence, observation, and information can be synonymous or used interchangeably. Also, don't forget that some of that data can be based on what is inferred and not directly observed. Once whatever data is collected, it must then be analyzed. When you analyze, you are actively going over all the details of your data and noticing any pattern or structure that may not be easily seen. Especially when data is organized in data tables and converted into graphs, this analyzation process becomes much easier. It is through analysis that discovery can be made. However, always make sure to allow the data to speak for itself and not to manipulate it or mold it to what you want it to say. This is especially easy to do with graphs. This is how we best interpret that data. We as scientists do our best to explain and summarize what the analysis showed. So, for example, in our lab experiment where we were testing the length of the rotors on our paper helicopters, we recorded the duration or time it took for each different size copter to descend or fall. From this data table, we can analyze or examine what the data is showing in relation to the variables of rotor length. A great template or formula to use to produce a written explanation is to use the CER model. That stands for Claim, Evidence, and Reasoning. According to the CER model, an explanation is composed of 3 parts: a claim that answers a question, evidence from collected data, and reasoning that demonstrates why the evidence supports that claim. By simply answering the following questions, one can compose a pretty good written explanation. So you ask yourselves, what do you know? How do you know that? And why does your evidence support your claim? For example, in our paper helicopter scenario, our claim is that the longer rotor provides more air friction. We found that compared to the short rotors, the long rotors allowed the copter to descend slower. This shows that the longer our rotors were, the more friction against the air there was and the slower the descent.